So this is the notes and examples for 5.1 perpendiculars and bisectors. So a perpendicular bisector combines two vocabulary words that we have had in the past. So we have already learned what it means to be perpendicular. So perpendiculars intersect to form a right angle. So at the intersection of our perpendicular bisector and the original segment, you are going to have a right angle, and it's going to happen at the midpoint. So our intersection itself is at the midpoint. So our midpoint is the intersection location. And remember that the midpoint will divide into two congruent segments. So those two pieces on either side of the midpoint will be congruent to each other. Our next vocabulary word is equidistant from 2 points, and it is exactly what it sounds like. It is equal distances from one point to another. So in this particular case, our common point is the C, and our 2 points that we are equal distances away from are A and B. So our point C is the exact same distance or length away from A and B. Keep in mind that this deals with equals, so you may have to apply the definition of congruent to get that the segments themselves are congruent to each other. So the lengths are equal, and our definition of congruent can give us that those segments are congruent to each other. In the next one, we need to know how to measure the distance from a point to a line. So there's more than one segment that can be drawn from a point to the line, and the one that you measure as the official distance is the perpendicular segment. So our distance is measured using that perpendicular segment. Equidistant from two lines, so we have two lines, and you're going to have the exact same perpendicular segment measurement between them. So our perpendicular bisector theorem, if a point is on the perpendicular bisector of a segment, then it is going to be equidistant from the endpoints. So in our diagram, our point B happens to be on the perpendicular bisector. Our endpoints of the original segment are at A and C. So we're told that we have a perpendicular bisector, and we're going to get those equal distances. So from B to A is exactly the same as B to C. Keep in mind that our definition of congruent, because those are equal distances, those segments will be congruent. The converse just turns it around. So if we know we have the equidistant from one point to two others, so we have point B is the same distance from A and C, then that means that point B has to be on the perpendicular bisector of that original segment. Now, when we draw in those equidistant pieces, we actually create a triangle. The triangle that has vertices at A, B, and C is an isosceles triangle. And remember that with isosceles triangles, we can use the base angles theorem. So we actually get a set of congruent angles at A and C. We also are going to use the fact that because of an isosceles triangle, anytime we have our vertex angle perpendicular to the base, that segment is always going to be the perpendicular bisector. Our angle bisector theorem, so remember our definition of angle bisector is a ray that divides our angle into two congruent angles. So our point D is on the angle bisector, so that ray AD bisects our angle BAC. And it turns out that any point that is on this angle bisector is equidistant from the sides. And remember, when we're measuring distance to sides, which are segments, that we're going to have to use those perpendicular measurements. So those equidistant pieces are the perpendicular measurements from our point on the bisector to the sides of the angle. It also works the other way. If we have that equidistant, or if we have that those segments are congruent, because we can use our definition of congruent to get back to the equidistant, then we know that that common point is on our angle bisector. So we're going to use this knowledge to answer some questions. So keep in mind that when we're working with relationships of items, that lengths are equal, but objects like angles and segments are going to be congruent to each other. So if it asks for the relationship between objects, you should never tell me that they are equal. Objects are not equal, numbers are. So the first relationship that we're looking at is the relationship between the segments AD and the segment BD. So the segment AD and the segment BD. And this is actually going to use the definition of bisector. So our definition of bisector tells us that we are dividing that into two congruent pieces. So these two are congruent to each other. In the next one, we're looking for the relationship of angle ADC and angle BDC. Now, one of those has an indicator. The angle BDC is indicated as being a right angle. That tells us that we have perpendicular. Perpendicular gives us more than one right angle. So we also happen to have a right angle at ADC as well. And we have a theorem from the past that says all right angles are congruent. So our relationship for this set is that those particular angles are congruent. The last question wants to know the relationship for the length of the segments AC and BC. So keep in mind that we have a perpendicular bisector. So this line is our perpendicular bisector. And we have this point C is on our perpendicular bisector. And we have a new theorem. So we have a theorem. It is the perpendicular bisector theorem that says if a point is on the perpendicular bisector, then it is going to be equidistant from the endpoints. So our endpoints happen to be the A and C. So C is our point on the bisector, and A and B are the endpoints. So we are equidistant. This is going to make AC equal to BC, and then we have to use the definition of congruent to get that the segment AC is congruent to the segment BC. So in each of these problems, the relationship is that the objects are congruent to each other. So in each of these problems, the relationship is that they are congruent to each other. And in problem 5, our explanation of our answer is this new perpendicular bisector theorem. Our next question, Sorry about that. No idea why this keeps not wanting to work. So there we go. Sorry about that glitch. So we have a angle bisector this time. So we are told that the ray PM is an angle bisector. So the angle that we're bisecting is the angle LPN. So we're looking for a relationship. The first one is with a set of angles, and notice that within the name of the angles, we have P and M. That's our bisector. And then one of them has L, which is the left side of our angle, and the other one has N, which is on the right side of our angle. So this is going to use the definition of angle bisector, which lets us know that we divide into two congruent angles. So those particular angles have a relationship that they are congruent to each other. So these angles are congruent to each other. In problem 7, we're looking for the relationship with the distance between a point and some rays. So it turns out that these are the sides of the angle. And we have this point M. So it turns out that M is on the angle bisector. So our point M is on the angle bisector. We have an angle bisector theorem, which says that when we're on the angle bisector, it is going to be equidistant from the sides of the angle. So this means that my distance from P to the sides, now keep in mind that we have to look at those perpendicular segments, and that's what we have. So this perpendicular segment from M to PL and the perpendicular segment from N to PN are going to be congruent. So we're going to be equal distances. So ML will equal MN. So our related is that they are equidistant, which makes them equal. We're going to use the perpendicular bisector for this next set. So when we look at this set of problems, our perpendicular bisector is indicated in a couple of ways. The first two questions indicate our perpendicular bisector by telling us the perpendicular and a set of congruent segments. So perpendicular and a set of congruent segments, as opposed to question 18, where it just tells us that we have the perpendicular bisector. So remember, we have our perpendiculars. So there's our right angle. And we have our bisecting. This is where we get those congruent segments at V. So that's our bisecting. So that makes this line SV the perpendicular bisector of the segment RT. So we're going to use our information in order to find our measurements. So for this first one, we're actually going to use our definition of bisect. So VT is going to equal VR. And if we look at the diagram, VR happens to be 8. So the answer to this question is also 8. In the next one, the segment we're looking for, SR, happens to be the distance from a point on the bisector to an endpoint. So we're going to use our perpendicular bisector, sorry about that, our perpendicular bisector theorem. So S to R is the same as the length from S to T, and that happens to be 17. So both of those segments are 17. Problem 18 says that we know that that line SV is our perpendicular bisector of RT, but now it wants to know, because the segment UR equals UT, which both equal 14, they want to know what we can conclude about point U. So the information that we're given lets us know that U is equidistant from the endpoints of RT, and we have the converse of the perpendicular bisector theorem, which says that when this happens, we get that our point is on the perpendicular bisector. So this means that our point U is actually on the line SV. So our conclusion here is that point U is on our perpendicular bisector. So if you were to extend the perpendicular bisector, point U would actually be on it. In the next one, we are going to use angle bisectors. So within the question, you are told that you have an angle bisector. So this ray that we have in our picture, JN, has divided our original angle into two congruent pieces. And now we have our theorem that we can use. You're also going to notice that you have these statements about segments being perpendicular. So there's an important need for that information. And remember, with perpendicular bisectors, angle bisectors, so our angle bisector theorem is that if it is on the angle bisector, then it's going to be equidistant from the sides of the angle. So when we are measuring this equidistant information, we have to make sure that we're dealing with perpendicular segments. So that's why they have to tell us those perpendicular segments. That equidistant has to be perpendicular segments. So when we look, they tell us the perpendicular at NP and JP, so we get that right angle to the top side. They tell us the perpendicular of NQ with JQ, so that gives us our perpendicular with the second side. And now if we use this theorem, because point N happens to be on our angle bisector, it makes those distances to the sides of the angle equal. So these distances are equal, and NQ is also 2. So these are equal distances, and both of them are 2. In the next one, we're once again given perpendiculars, but this time we're told that we have equidistances. So M is equidistant from the sides of the angle. So if we look at the first one, it's going from point M over to the top side, and MK is going from M perpendicular to the bottom side. These are both 6. So we have that equidistant, and we can use the converse of the angle bisector theorem to get that this is going to make this common point of M on the angle bisector. So our conclusion about point M is that it is on the angle bisector. So if you were to extend this angle bisector, point M would be on it.